Now let's learn insertion sort algorithm. Below I will write a sorted array and we will add 15 to this array without modifying its sorted order. So, to which index should we add 15? 15 is larger than 12 and smaller than 18. It should be located after index 2. But how do we insert 15 to our array? The last element, 33, is larger than 15. So we need to shift 33 to the next empty index. 33 should be shifted to this index. And we compare 28 with 15. Because 28 is larger than 15, we shift 28 to the next index position which is occupied by 33 before. Then we compare 23 with 15, and because 23 is larger than 15, we shift 23 to the next index position which is occupied by 28 before. Then we compare 18 with 15, and because 18 is larger than 15, we shift 18 to the next index position which is occupied by 23 before. Now our x variable shows index 2 and we insert 15 to the position x plus 1 which is third index. And after we insert 15 to our new array will look like this. Now let's add a number to a sorted linked list. And we want to add or insert 23 to this linked list. In order to add 23, we need two pointers, and these pointers will be A and B. At first, B will be initialized to null, and A will point the first element in the list. A and B are pointers. Now we compare 23 with the data elements pointed by pointer A, which is 7. And because 23 is larger than 7, first we bring pointer B to the position of A, and we move the pointer A to the next node. Below we can see this procedure. B points the first index, B points the first node, and the A points the next node. Now we compare 23 with the data elements pointed by pointer A, which is 11. And because 23 is larger than 11, first we bring pointer B to the position of A. And we move the pointer A to the next node. Now, again, we compare 23 with the data element pointed by a pointer A, which is 15. And 23 is larger than 15, we need to move B to the position of A. And we move A to the next node. And now we compare 20 with 23. And 23 is larger than 20, we move B to the position of A. And we move A to the next node. Now 23 is not larger than 25, so we stop. Now we create a new node called temp. And we put 23 in the data section of our new node, 23, and B points the new node, and temp points to the next node. As a result, if we use arrays, in order to insert a new element in a sorted array, we do not look for a suitable position. We go to the last element, 33, and shift these elements one by one to the right. But for linked list example, we are looking for a suitable position, which is after B. Now let's look at our time complexity. In the array example, we shift the elements. How many elements did we shift? It depends on the number of elements. If we have m elements in the array, we can shift at most m elements. So our time complexity becomes order m for array example. And this would be the worst case. But we have the possibility that we may not make any swaps at all. So our time complexity can become order 1, which is constant time, and this becomes our best case. In the linked list example, we are looking for suitable positions, and if we look for m elements, our time complexity becomes order m. Also, order 1, which is constant time, is still be our best case scenario. Now let's sort an unsorted array written below. We will sort an unsorted array by using InsertionSort algorithm. For our InsertionSort algorithm, we will assume that our first element is in sorted order, and we will put a line between 13 with the rest of the array. What we are going to do now is to take an element from the right side of the line and put it to the left side of the line. At first, we take 10 and put it under 13, as shown below. Now, the left side of the line becomes larger. And because 13 is larger than 10, we shift 13 to the right and we put 5 to the first index, and new array becomes as below. The procedure that we did above is called first pass, and we made one swap and one comparison in total. Now let's take 12 from the left and put it to the left side. And now our array becomes larger. It can contain 3 elements from the left side, and in the left side 13 is larger than 12, so we shift 13 to the right side and our array becomes like this. And this procedure can be called as second pass. And we made 2 comparisons. We compared 12 with 13 and we compared 12 with 10, but we only made one swap. One swap, 2 comparisons. But at most, we assume that we can make 2 swaps. So in this example, in the second pass, we can write the number of swap as 2. Now we can move to our third pass. And in the third pass, we put 8 to the left side of the line and we compare 8 with 13. 13 is larger than 8, so we shift 13 to the right index. Then we compare 12 with 8, and because 12 is larger than 8, we shift the 12 to the next index position. And last, 10 is larger than 8, so we shift 10 to the next position and we put 8 to the first index. And now our array becomes like this. And this is our third pass. Now the left side of the line has 4 elements. We have only 1 element on the right side of our line. So we take 7 from the right side and we put it to the left side. And now we compare 7 with 13. 13 is larger than 7, so we shift 13 to the right index, and 12 will be shifted to the right index, and the 10 is larger than 7. 10 also goes to the next index, and 8 goes to the right index. And now our array will be like this. And this is called as fourth pass. I also forgot to mention the number of comparisons and the swaps in the third pass. In the third pass, we made 3 comparisons and 3 swaps. And in the fourth pass, we made 4 comparisons and 4 swaps. Now we sorted our array 7, 8, 10, 12 and 13. We have a sorted array. We will make an analyze right now. But the analyze that we are going to do is the same that we did for bubble sort. The number of passes is 4. We had 5 elements, so we made 5 minus 1 passes. If we had m elements, we would make m minus 1 passes. And the number of comparisons is 1, 2, 3, and 4. If we generalize the equation for m elements, we can use this equation. 1 plus 2 plus 3 plus up to m minus 1. And the sum of these elements are m minus 1 multiplied with m divided by 2 equals to m square minus m divided by 2. And we can write this equation as order m square. And our time complexity becomes order m square, which is quadratic time. Also, the number of swaps is 1 plus 2 plus 3 plus 4. And these numbers comes from, in the first pass we made 1 comparison and 1 swap. In the second pass we made 2 swap and 2 comparison. In the third, 3 comparison. And at the fourth pass we made 4 comparison and 4 swaps. So the number of swaps is 1, 2, 3, 4, 5 elements. Also, we can generalize this formula for m elements, and the number of the swaps for m elements will be m minus 1 multiplied with m divided by 2, which equals to m square minus m divided by 2. Normally, when we apply bubble sort, at the end of the first pass we obtain the largest element in the array. In the second pass, we obtain the second largest element in the array. In the bubble sort algorithm, if you remember, at the end of the first pass, we obtain 12. So 12 is the largest element in the array. So at the end of the first pass, we obtain the largest element in the array. And at the end of the second pass, we obtain the second largest element, which is 11. So we obtain 2 meaningful numbers at the end of each passes. But for insertion algorithm, we do not obtain any meaningful numbers at the end of the first pass or second pass. At the end of the first pass in insertion algorithm, we only obtain 10 at the beginning. The 10 doesn't mean anything to us because the smallest element is 7 and the largest element is 13 and it's located in the second pass. So in the second pass, we do not obtain any meaningful numbers. The difference between the bubble sort and insertion sort is at the end of each pass, we can obtain meaningful numbers for bubble sort, but we do not obtain any meaningful numbers in the insertion sort. When we apply insertion sort for an array, we need to shift the elements. Because of this issue, insertion sort algorithm is used in linked list. Now we write our codes. Actually, before diving into the codes, I want to give an example. By using this example, we will write our codes. Below, I will give an array of size 7. We have a sorted array until 6 index. Our numbers are sorted between 0 and 5. And we have a sorted array like 8, 10, 14, 16, 20 and 23. And 12 is located at the wrong position. And our variable I points to the last element, which is 12. And we need to compare 12 with 22. For this, we need an extra variable called j. And this j will point 22. This j will point 22, which is located at I minus 1. So we can write our code as j equals to I minus 1. And we need to assign the value of 12 to a variable called data. So we can write our code as data equals to d of I. I assume that our array name will be d. At the ith index we have 12 and we will save this 12 to a variable called data. And if day of j, which is 22, if it is larger than 12, we need to move 22 to the right index position. And we make this by writing this line, j plus 1. So in this example dj plus 1 which equals to 12, and the day of j contains 22, and we assign 22 to 12. 22 comes here. Also, we need to increase j by 1 in order to show 20. And we need to make these comparisons and shiftings in the while loop. To implement this, we have to write this line. At the end of the while loop, when j comes to the index 1, which contains 10, we stop because 12 is larger than 10, and we put the data value to the j plus 1 index position. And we can do this by writing this line after while loop. But let's assume that instead of using 12 at the index position at 6, we can use 6. We can use 2. And this time, when we apply this algorithm to our array, j will come to the index 0. And at index 0, j contains the data element 8. And 8 is still larger than 2. So, if day of j larger than data, we have decreased j minus 1. But if we decrease j on this position, j becomes minus 1, which is invalid index position. So we need to apply this while loop until j larger than minus 1. So we need to update the while loop like this: while j larger than minus 1 and d of j larger than data. Also, we need to add a for loop to represent the passes in our algorithm. So we add for loop at this position. And the for loop will start from 1 because we already assumed that the first element in the array is in sorted order. I is less than the number of elements, which is m I plus plus. Now we can implement our codes to Xcode to see our results. At first, I will include IOStream library, and I want to use namespace std. And now we can implement our function. The InsertionSort algorithm or our function will not return any value, so the return type will be void, and the name can be InsertionSort. And also we will take an array as a parameter like we did in the bubble sort. Also the number of elements, which is m. So I want to declare variable called I for our for loop. And I will start from 1. I is less than m I plus plus. And inside for, first j should be I minus 1. And d of I should be assigned to data variable. After we assign our value to data, we can implement a while loop, and j should be greater than minus 1, and d of j should be larger than x, should be larger than data. And if the previous element is larger than the last index, we will swap their positions, and dj plus 1 will take the value of d of j. Also, we have to decrease j by 1. Outside of the while loop, we can write our data to the position of j plus 1. Now we can implement our main function. Inside the main function, I will create an array of size 10, and the values will be, and the length will be 10, and we can call InsertionSort algorithm. After we applied the InsertionSort to our array, we can print the values by using a for loop. Okay, let's run our program. And we have to sort this array by using InsertionSort. 9, 12, 14, 15, 23, 32, 45, 56, 61, and 78. Okay, our algorithm works fine. We sorted our array. Now let's make an analyze for adaptive and stable features. I want to give an example to understand the adaptive and stable property or feature of InsertionSort algorithm. And our array will look like this: 2, 5, 8, 10, and 12. In this array, which is a sorted array, first we assume that 2 is in sorted order. And we take 5 at first and compare with 2. 5 is larger than 2, so we do not make any swaps. Then we take 8 and we compare with the left side. 8 is larger than 5 and 8 is larger than 2, so we do not make any comparisons. And then we take 5 and we compare 10 with the 2, 5, 8, and then we take 12 and we compare with the left side of the table. So in the sorted array, we made 0 swaps, and in total we made 4 comparisons. So in this example we had 5 elements and we made 4 comparisons. So if we assume that we have m elements, we would make m-1 comparisons. So our time complexity based on the number of comparisons will be order m. And we made 0 swaps, so we can write our swaps as order 1, which is constant time. Based on this observation, we can say that when we have a sorted array, we consume less time, so we can say that InsertionSort algorithm is adaptive. Also, if you remember, we used a flag variable in bubble sort to make the bubble sort algorithm adaptive, but we didn't use any flag on this algorithm. So InsertionSort algorithm is adaptive in nature. We do not need any extra variable. So as a result, we can write our time complexity values like this. Now let's check the stable feature. We can use this array in order to understand that the InsertionSort algorithm is also stable like bubble sort, and our array numbers will be 3, 5, 8, 10, 12, and 5. And at first we will compare 5 with 12, and because 12 is larger than 5, 12 comes to this position. And then we compare 10 with 5, and 10 is larger than 5, also 10 moves to the next position. And 8 is larger than 5, so we move the 8 to the next position, and 5 comes to this position. And then we compare with this white 5 with the blue 5. So this 5 is not larger than the blue 5, so we do not make any swaps. So first 5 doesn't change its position. So we can call the InsertionSort is stable. And in the next lesson, we will compare bubble sort and InsertionSort. We will compare their minimum comparisons, maximum comparisons, and based on their swaps and their adaptive and stable features. I hope you liked the video. See you next time.